So good afternoon, everyone.
Good afternoon.
And Professor Wieman, we are so grateful to have you, and thank you so much for accepting this invitation to grace this event. It's a real honor for all of us.
My first career retirement was, I think, at 16 or 17, where I decided, okay, at that point I was really focused on chess, and I was, I wasn't top of the nation, but I was top of, in the younger age group, top of a quarter of the nation at that point. And, and I sort of looked at what, that time they're going to chess tournaments and all these old guys sitting there smoking all the time, and I didn't like smoke, and they didn't seem like much of a way to be spending your life. It wasn't really much value to humanity, so I decided, okay, I've reached as good as I want to get in chess. I'm going to switch to something else. Then I was focusing a lot of, I was doing academic stuff too, but frankly, and I went off to MIT, but I was very interested in tennis, and I was on the team there and so on. And then my arm gave up because I was practicing too hard. And so, okay, so then that was cutting down options here. But, what really happened to me was I got involved in working in a physics lab, doing research, by just a lucky set of circumstances, really in my very first year at the university, which was quite unusual. And I got an unusual amount because of some people quitting and so on. I got an unusual amount of responsibility there. So, at some level I was doing real physics. And I just found that so much more fun and interesting than studying all these academic things. And the reality was I just about flunked physics in my first year. So by normal standards, I was a dismal failure at it. But I could see, and the people I was working with could see, okay, working in a research lab, he works really hard and he thinks about things. And so for me, that was just so much more rewarding. So I said, that was really then, okay, this is great. And, it was something I enjoy doing and can do. And so I pretty much did that forever just on that basis. In retrospect, I think if I'd gotten a chance to work in a biology lab or chemistry lab or a geology lab, I probably would have ended up being just as happy. Although, I have, certain things about physics, I'm sort of looking at underlying fundamental principles kind of appeal to my, my personality. But that was really what made the choice. And then my own fun, just my own personality is to, when I get an interest in something, to really focus on it. And that, started out when I was 6 years old, and so, but once I started, picking physics research, that's what I did. And I took I always like to tell students, and this won't work very well for you, is that you should never let courses interfere with getting a good education. And in my case, I, spent absolutely as much time as I could in the physics. I took the absolute minimum of courses and did the absolute minimum of work in them, and as a result got an extremely good education, but not by normal standards. Pick the right area of research and pick the right problem to work on. Now, I've been known for, and I've been successful for being very effective at picking the right area. And I'll explain how I made those choices. I think a lot of people tend to just kind of they'll go and they just follow their experiences, what they knew about it, and they'll just make tiny little increments in it. Whereas, so the first criteria that gets overlooked, but I want to stress to people, is that what defines important research? The only thing that determines whether something's good research or not is whether the community of other researchers decide it's good, okay, and it's important. And then the other thing that's important is you always have to make this judgment about how big a leap you're going to make. If you make a tiny little leap, well, a whole bunch of other people are doing that already, so it's not going to single you out as an important researcher ever. You're just going to be part of the pack. But on the other hand, it's important to not take too big a jump, because you have to be in an area where people, they're making the judgments. We'll see this as an important advance, but it won't be so far that they can't, if it's way beyond what they were thinking about, they won't really appreciate that it's an advance. So it's a little ways ahead, but not too far ahead. I guess the one other thing that's very important, and I see this very much in good scientists, but it's true in people in every field, if you know what to look for and look carefully enough, which is that I don't know a good way to say this, so I'll be sort of long convoluted, but they sort of reflect on what they're doing and think how to improve it in a very much ongoing basis. And so whether that's studying and learning something, instead of just kind of doing the problem sets and what you're supposed to do, you sort of always are regularly stepping back and asking yourself, do I really understand this? Can I see how this would work in other areas? And gee, if I don't, how can I think about this better? Where can I go learn more about it? And, then you get to science and you think about, I'm doing this experiment. Is this really working well? Or maybe I should be is there a better way I could be doing this? And this kind of continual cycle of testing and then improvement. So this issue of when do you give up, okay? This is one that's one of the most critical decisions in science, and being a successful scientist is knowing the right time to give up. And there are countless examples of people who didn't give up soon enough. They spent their whole career kind of going down a dead end. There are other examples of people who gave up too soon, that one can look back and they had gotten 90% of the way, 95% of the way to an enormously important discovery, and they stopped, and now other people came along and got Nobel Prizes for it. So, I cannot give you any rule on that. I can just say that the good scientists have made better decisions on every scientist faces those questions, and the ones who are more successful pick better answers. Now, it may be a coincidence. The ones who randomly pick better answers ended up being better scientists. But yeah, I can't give you an answer on that. It's like I say, it's a really hard question, and I just don't know rules to use, to be honest. One thing I can say is that I designed for long, difficult experiments. And what I mean by that is that when I would think you'd do some experiment and it would give something and it wouldn't be what you'd hoped for, but these oftentimes it's because there were new unknown things that showed up to be important. So, but I would rather, and this is particularly important when you're working, you have graduate students working for you and postdocs, and they need to have something to do to graduate or get jobs as postdocs. And so I would really build into my design a lot of thinking about, okay, how could this not work? What are the possible ways that this is going to fail? And if it does fail, in this way, how can I make sure that something comes out of it? And so that was almost always from the perspective of, okay, if this is going to fail, it's because I don't know certain things. There are certain unknown ways. I mean, in the case I spent a lot of time on the way atoms behave when you get them, 100 times colder than anybody had studied atoms interacting with each other before. So we didn't know, at all what that's going to happen. So that could mess up where we were trying to go to. But how can we make sure that we at least have learned something more, measured something new that would be produced? So a failed experiment would be failed only in the extent of not reaching some ultimate goal, but it would be a successful experiment at giving us new information, new physics, something that would be a PhD thesis, would be publishable, even if it wasn't going to be wildly exciting to people. It would be some clear step along the way with some clear publishable results. That's again a personality issue. I think most good scientists have quite a high threshold for frustration, because most of the time in science things don't work. It wouldn't be science if it was. Well, I would say if you find out it always works, you're picking bad problems, because it means too much is known about that problem already. You're not going to make any new advances. It's the interesting problems, there's unknowns, okay? And so most of the time things don't work because there's new unknowns you're discovering the hard way. And so, I think mostly people have a chance to start doing that, and I see some of them that started working in this and decide, gee, I don't like this. I'm going to go into something different. And so it's kind of a selection. It's, as far as I can tell, it's not something you adapt to. It's something you're selected for if you go into science. The way I explain it to every general audience, and a particularly quick answer, is that back in 1924, Einstein, building on some work of Bohr's, predicted that if you could get atoms really, really, really cold, they would turn into a completely new form of matter. Sort of like, water freezing into ice, but much more exotic than that, okay? So what we did was manage to figure better ways to hold atoms so they didn't heat up, so like a super thermos bottle, and new ways to cool them to get them down to much colder than anybody had ever got before. There's this absolute zero, which is the coldest you can get to. We're down to less than 1/1,000,000th of a degree of an absolute zero. That's where Einstein predicted this thing would happen, and it did happen, okay? What was wonderful about this wasn't that Einstein predicted it, it was actually that it has really strange, fascinating properties. We think of the way things behave, in the world we see, but we also from physics know that if you get deep in the tiny, tiny, tiny level of inside atoms, they behave totally different. They go by the laws of quantum physics, which are very different than the laws of how things behave around us. Bose-Einstein condensate basically takes those weird laws of quantum physics and puts them in a much larger size scale. So up to the size of a human hair, which is, millions, billions times larger than they're usually seen at. So that means people can poke and prod and study these laws of quantum physics in a way that's never possible before. So is this beneficial to humanity? Well, it's not going to cure cancer anytime soon. So I'd have to say it's a very limited benefit. It has, though, I will, since I get this question a million times, try to come up with some reasons for it. So it was immediately useful for exploring an area of physics, which was relevant to technology, because in building better computers and circuits and phone, all the fancy electronics and phones, the key idea there is to make things that electrical components smaller and smaller and smaller and smaller. That gives you more and more capacity. And that works great down till you start getting down to a size of a few atoms, and suddenly you're not dealing with behaviors like we're used to seeing with electricity flowing. You're now down into these weird quantum mechanical rules of behavior, and things are really weird and different. And it turns out that, physicists it was easy, relatively easy, to study stuff at the big size scales. That's, you can do in introductory labs, playing with wires and stuff. And it was relatively easy to do at the tiny scale. You could see how atoms behave. This intermediate region, where you're making the transition between these two very different laws of behaviors, that is somewhat, but when we got Bose-Einstein-Conze, was a very fuzzy area of people weren't all that sure how things would behave, but it was important because they were starting to build components, trying to build, computer chips that were down at that size scale. So it helped people make a lot of better understanding of that. So that's about as close as I can get to something that is going to help humanity. Okay.